Hello friends, last class I discussed about the introduction to digital electronics. So digital electronics means what I told, the digital thing that is associated with the digits, okay, or binary number 0 and 1. So these 0 and 1, these binary numbers are associated with the computer only. If you go into the real life, in real life there is no concept of the 0 and 1. So if you want to deal any number inside the computer system, so for that binary number is required. So apart from the binary number, there are lots of number system in our physical world. Okay, so today I'll discuss about the number system and how each number system can be converted into the other number system. Okay, so in our daily life, if you see, so many number things are there: decimal number, decimal, hexadecimal, binary, octal, BCD. Okay, so before going to this, these are the types of the number system which are commonly used in our daily life or in computer, any different net systems, right? Number systems. What is the number system? Number system is a set of the numbers or values, okay, which is used to represent any kind of the physical quantity, right? Physical quantity means, suppose how many apples are there, right? So apples, these are the physical quantity, but to represent this physical quantity we need some numbers, right? So 10 apples are there. So decimal number, that is used for the human interaction mainly, decimal number. So if someone used to tell how many apples are there, so we used to tell like the 10 apples, two guys, a car has four wheelers, four wheels are there. So these are whatever things we are dealing with human to human interaction. For human to human interaction, what are the number system are used? These are the decimal number system. Now if we go into the any kind of the system, if you want to enter those physical quantity into the system, okay, so for human understanding, decimal human only understand the decimal number, but computer will not understand the decimal number. It only understand like a binary number, or if inside the computer hardware part is also there. So for hardware, the hexadecimal number is the useful, and octal is also for dealing with the computer only. Okay, so if we suppose if we are entering any decimal number inside the computer, it will be stored as a binary number or 10 number or hexadecimal number. Inside the computer there are the two parts, right? So if you want to do anything inside the computer, one is the hardware, another is the software, right? So if you want to deal any number with the hardware, suppose microprocessor, microcontroller, these are the hardware components, CPU. So if we deal with this thing, so normally numbers are stored as a hexadecimal number, okay, or octal number. But if you want to write anything inside the computer, if you want to write or read operation, if need, the binary number is required, which is dealing with the software portion. Okay, then the binary number is required, 1 and 0. This binary number is required. Okay, binary number is required. For this is mainly hardware related. Okay. This is a physical world, related to physical world or real world. This is mainly related to software. Okay. So two different kind of the languages used to prefer. One is the machine level language, and another is the high level language. For high level language, mainly the software binary number is used. For machine level language, normally hexadecimal number is used. To represent this number, how can you represent this number? To represent this number, one term is the base or radix. Okay, base or radix. This is a term to represent how many distinct numbers are there, how many numbers are there in each and every number system. By using the base or radix, we can calculate. Okay, so this is the basic term to represent any kind of the number system, base or radix. To represent any kind of the number system, or how many numbers are there in any kind of the number system, this thing can be calculated by using the base or radix. Okay. For case of the decimal, okay, for case of the decimal, For case of the decimal, the base is, this base is 10. Okay, this base is 10. So when you write any number, so the 10 should be write as a suffix. Okay, subscript or suffix. Okay, so 10 means if base is 10, then suppose the formula is there, if base is n, then how many distinct numbers are there in any particular number system? If base is 10, distinct number. Distinct numbers, how many distinct numbers are there? 0 to n minus 1 distinct numbers are there in particular number system. Okay, in any number system, suppose n is the base. So in that number system, how many distinct numbers are there? 0 to n minus 1 distinct numbers are there. Okay, so for case of the decimal, the base is 10. So how many numbers are there? 0 to 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This much distinct numbers are there in decimal number system. So normally it's on if you write suppose 0, if you write 9, it normally denoted as a decimal number. Only required to put any base for case of the decimal number. Okay, because all the physical world numbers are related to decimal number. For decimal number, the base is not required to put. Okay, so next is the hexadecimal. For hexadecimal, hexa means the base is 16. Okay, the base is 16. So how many now distinct numbers are there? 0 to 15 distinct numbers are there. But I am writing here 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So 10. After 9, you will not write 10. Okay, 10, 11, 12, 13, 14, 15. Okay. So this thing. So 10 is also there in the decimal. Okay, 10 is also there in decimal number. Suppose 0 to 9. If you represent 0 to 9, how can you 10 consist of 1 and 0? 1 and 0, these are already there. 1 and 0, these two distinct numbers are already there in decimal. Okay, so to understand this thing, okay, so to understand this thing, so if you after that, so if you 0 to 9, 0 to 9 decimal number, 0 to 9 hexadecimal number, almost both are same. Okay, if you go to the 10, 10 as a hexadecimal but 10 as a decimal, both are different. Okay, that will tell later. Okay, 10 as a hexadecimal and 10 as a decimal, both are different due to the base, due to the distinct numbers. Okay, so if you convert hexadecimal to decimal, 0 to 9, both are same for decimal and hexadecimal. But if you after 9, if you go to 10, okay, so 10 consists of 1 and 0, this 1 and 0 that is already there in decimal, but that 10 and this 10 both are different. Okay, both are different. So for that, here to represent, to distinguish this number, the 10 will be B, A, 11 will be B, 12 will be C, 13 will be D, 14 will be E, 15 will be F. Okay, so after 9, directly it will come into the A, B, C, D, E, F. After F, then 10 will appear. That 10 is different from that 10. Thus, if you write in sequence wise, that 10, the position of the decimal 10 and position of the hexadecimal 10, both will be the different. Okay, so this is for application specific. For different application, I have to use the hexadecimal number. So I will come to the binary later. So for case of the octal, so for case of the binary, all of you know. Okay, first I will discuss binary. So binary means 2, base is 2. Okay, base is 2 means how many distinct numbers are there? 0 to 1. 0 to 1, only two numbers are there, 0 and 1. So that is mainly used for digital electronics purpose, 0 and 1. Okay, then come to the 8, octal. Octal, that is related to 8. Okay, so base is 8. So how many distinct numbers are there? 0 to 7. 0 to 7 means, here I am writing 0, 1, 2, 3, 4, 5, 6, 7. Okay, after 7, there will be no concept of the 8. So in case of the decimal number system, 8 is there. After 7, 8 is there, then 9. Then 10 will appear. Okay, so because the base is 10, so total 9 distinct numbers are there. Right, but in case of the octal, total 8 distinct numbers are there, right? 0, 1, 2, 3, 4, 5, 6, 7. 0 to 7, this 0 to 7 and this 0 to 7, all are same. Okay, but when you come to the 8, okay, so 8 after 7 8 is there in case of the decimal. In case of the hexadecimal also after 7 8 is there, as there are the 16 distinct numbers. But in case of the octal, after 7 there is no concept of the 8, because 8 there is no concept of the 8. It is not there in the list of the distinct number. After 7 again 10 will appear, because the 10 inside the 10 1 is there, also 0 is there. 1 and 0 both are there in octal number. So in case of the octal number, after 7 it is ended. So if you want to represent any 2-digit number, then so in between 0, so by using these 7 8 distinct numbers, you have to design the 2-digit number for case of the octal. For case of the decimal, so by using this 10 distinct numbers, you can design 2-digit number, 3-digit number. For case of the hexadecimal also, by using these 16 distinct numbers, you can design for 2-digit and 3-digit decimal numbers. Okay. Now after 9, here 10 will appear, but after 9, in case hexadecimal, after 9 A, B, C, D, to represent these 10 and to distinguish this 10 and that 10, so this 10 is represented as A. Okay, and for here, because after 7 there is no 8, because 0 to 7 all are now, all numbers are same for 0 to 7. Okay, all numbers are same, right? So I think it is clear. So by using base, you can calculate. Main formula is there. If base is 9, base is n, total how many distinct numbers are there? Total n minus 1 distinct numbers are there. Okay. Now BCD number. BCD number that is represented in the form of the 8421. 8421 is a 4-digit. In case of the BCD, there are 4 digits. 4-digit BCD number consists of 4 digits. Okay, how will represent it? And this 4 digit contain 1 and 0 only, no other numbers are there inside the 4 digits. Okay, how can so suppose random 4 digits are there, in these 4 digit 10 numbers are there, distinct numbers. Okay, by using the 10 distinct number, you can design lots of 4 digit numbers, right? Lots of 4 digit numbers. Okay, but there is a format, 8421 format, right? These are the weighted. Suppose 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. This is called the weightage. Okay, by using this weightage, okay, 2 to the power n minus n, 2 to the power n weightage, we can do this thing. 2 to the power 0, 2 to the power 1, 2 to the power 2, 2 to the power 3. So after 2 to the power 3, 2 to the power 4 will appear, but that will not consider. In case of the BCD, only 4-digit number should be there, but this 4-digit consists of 1 and 0 bit. So by using the 1 and 0 bit, we can design lots of 4-digit numbers. But so how that 4-digit number will be? The format of the 4-digit number, that is like a 8421 format. This is the weightage. Okay. So BCD number that I will discuss later. Okay. BCD number. Now I am coming to the conversion. Okay, conversion between different numbers. Conversion, when conversion is required, so if want to suppose in computer, computer only understand the hexadecimal and binary number. So for that, inside the system, the converter should be there. This converter converts the decimal to the binary number, hexadecimal number, octal number, or octal number to octal number, decimal number, and binary number to the decimal number. Okay. So here today I will just discuss 3 decimal numbers. That is decimal to, decimal is a basic decimal that is for human interaction. So decimal to binary, then decimal to octal, then decimal to hexadecimal. These 3 I will discuss. Okay. Right. So, so this conversion I will discuss today, and tomorrow I will discuss binary to decimal, octal to decimal, hexadecimal to decimal. Okay. First I will discuss this one. How we will convert decimal number to the binary number. Okay, so 110, so this is a 1 decimal number, right? So the decimal point is also there, real number is also there, fraction number is also there, 29.15. Decimal to binary. So decimal is the basic number, right? You have to convert to the other number system. So first you have to check the other number, the number, whatever the number you are, the source number. This is the source number, this is the destination number. So you have to check the base of the destination number. Okay. So base of this destination number, base of the destination number is 2. Okay, so for that, if you want to convert decimal to any other number system, so for that, so what is the base of that other number system? That, so the decimal number should be divided by that base of that number system. Okay, decimal number should be divided by base of that number system, and that fraction number, that should be multiplied by base of that other number system. Okay, decimal number be divided by base of other number system. Okay, and the fraction point, so fraction number, that should be multiplied by base of other number system. Okay, right? So here I'll show this one, 29. Okay, so if we divide 29, so what is the base of the binary number system? 2. Okay, so if we divide 29 by 2, okay, if we divide 29 by 2, so you will get, okay, so you will get 14 as a quotient and 1 is a remainder. So this 14 you will put here and quotient you will write here. Okay, sorry, remainder will write here, right? So again, so it will be, the process will be continued till you are not getting any 0 or a number 0 or 1. Okay, because 1 will not be divisible by any number. So here now again 2. So if you divide 2 by 14, 7 you will get, right? So the 7 is a quotient, here you will write, and remainder you will write here. Again I have to divide 2, 7. So if you divide 2 by 7, so this 3 is the quotient and 1 is the remainder. Again I am dividing 2 by 3. If you divide 2 by 3, you will not get, at one time it will get, so 1 is the remainder and 1 is the quotient. So it is not divisible, right? If you divide 1 by 2, you will not get anything. So what is the equivalent, binary equivalent number of 29? So you have to write the digit from bottom up approach, like a bottom up, from bottom to up. Okay, so in 29, 10, that is equal to bottom to up 1, 1, 1, 0, 1. Okay, bottom to up you have to write. Okay, this is the decimal to binary number system. Now come to the fraction point, 0.15. Okay, so for fraction point you have to divide the number with base of the other number system. Okay, if you divide 0.5 into base is what? 2 for binary. So if you divide 0.1 into 2, so 0.30. So okay, so this 0 will be stored as a result, and you will take 0.3 here. Okay, 0.3 here will come. 0.3 again you have to do, divide, multiply by 2. The process will be continue till you are not getting 0 after the point. Okay, till you are not getting 0 after the point. Or if the process is same kind of the numbers you are getting, so you can stop the multiplication, right? So 0.30, it is 0.6. Okay, again the 6 will come here. 0.60 into 2, 1.20, right? Then 2 will come here. 0.2 into 2, 0.40. Then 4 will come here. 0.4 into 2, 0.80. Okay, right? Again here I am writing 0.80 into 2, 1.6. Now you can see if you 0.6 into 2, right? Same number you will get, 1.2 you will get. So you can stop up to here. The process will be continue up to here, because after 0.6, the same step is there, 0.6 into 2, 0.6, same thing is appearing. So you won't require to do further process. Okay. Now what will be the binary equivalent number of 0.5? You have to only consider the before the point number. You have to only consider this 0, 0, 1, 0, 0, 1. Okay. But for case of the integer number, you have written down bottom. You have to consider the bottom up approach. For case of the fraction number, you have to consider the top down approach. Okay, top down approach. So here we will write, so 0.15 decimal, that is equivalent to 0, 0, 1. Only you are considering this number, 1, 0, 0, then 1. Okay. So for number 1,101.001001, right? This is the decimal to binary conversion. Second one is the decimal to octal. Okay, decimal to octal. The number, suppose the number is 73.04375. Okay, this is the decimal number. Sorry, decimal number. Now 73 is the octal number, right? Okay, 73 is the octal number. Sorry, 70 is the decimal number. You have to divide the 73 by octal, because the base of the octal is the 8. The number, decimal number should be divided by the base of the other number system, 8. Okay. So if you take 8, if you divide 73 by 8, you will get, I think, 9. Okay. Sorry, 8, 9. Right. Okay. The remainder you will write here, 8 you will write here. Okay. And after that, again if you divide 8 by 8, so 8 by 8, here you will get 8, here it is 0. Okay. So here it is 0. So the quotient will write here. Okay. And sorry, remainder will write here, quotient will write here. Okay, that is the 73. Okay, so you have to write like this way. Okay, so for case of the this number 0.04375. Okay, so for that this should be divided into 8. For this fraction number, that that should be multiplied into the 8. Okay, sorry, here so the quotient that will write a remainder we want to write here, I forgot. So 7, 8, 9 is 72. So if you divide the 73 by 8, 9, 72, here we will get 1. Right? Again if you do 8, so the 8, here you will get the 8 and 9. One time it will get, and here will be 10. Here you will get 1, here. So the remainder you will put here, and quotient you will put here. Okay. So in this way, so 111 is the equivalent number of the 73 in the form of the octal, right? So for this case, 0.04375. So this is the fraction number that should be multiplied into base of the octal number system 8. Okay. For that, what you will get? 3.5 you will get. Okay. So now after 3.5, you have to only consider the 0.5 for multiplication. 3 will not consider. Okay. So 0.5, if you write here 0.5 into 8, so that will be 4.0. Right. So here you are getting the 0. So again you cannot multiply 0 with the 8. Again you will get the 0. If you multiply 0 with the 8, you will get 0. Right. So this is the same thing. So this thing you have to write like this way. Okay. Top down approach. So what will be the equivalent number of this thing? It will write like this way. 111.34. Okay, it will write like this way, 3 then 4. So this is the octal number of their corresponding decimal number. Last is the decimal to hexadecimal number. Okay, so the number is 250.437510. Okay, the same procedure, decimal to other number system. So the base is the hexa 16, so you have to divide 250 by 16. Okay, so here you will get the remainder as a 10 and 15 as a quotient. Okay, so you cannot divide the 15 by 16, right? So you have to stop the process here. So this will be like a bottom up approach. Okay, for case of the fraction number, again I have to multiply this number with the 16. So for this you will get the 7.0. So this thing is not possible. 0 into 16 is not required. Again you will get 0. This will be right like this way. Okay, top down approach. So for case of this number, real number, to write like this way, bottom up, right? 15, 10.7. But 15 and 10, okay, we cannot write 15 and 10 because 15 and 10, these are not there in the hexadecimal. So 15 can be represented as a F and 10 can be represented as a A. So this is the hexadecimal number for this. How I have written, because after 9 if you write 10, 11, 12, 13, 14, 15, it will like this way, A, B, C, D, E, F. Okay, 15 will be F and 10 will be A. So in this way you will get decimal to hexadecimal conversion. So for again I am repeating, if you want to convert any real integer decimal number to other number system, you have to divide those particular decimal number by the base of the other number system. And if you want to convert any fraction decimal number into the other number system, you have to multiply that number with the base of the other number systems, right? So next class I will discuss about this other number system conversion between other number system and the decimal number system. Thank you.